Hey guys, welcome to Pre-Calc lesson 9.2, Radians. And as you can see, we're really excited about radians. Okay, quick warm up here. I want you to evaluate sine 7 pi over 4. A little bit of a review from last year. So here's how we approach it. First of all, you notice pi over 4, and you recognize that as 45 degrees. You think back to your special right triangle, 45, 45, 90, and you recognize sine of 45 is 1 over square root 2. Almost done. We have to take into consideration it's 7 pi over 4. So ASTC, 7 pi over 4 puts you in the fourth quadrant. That means cosine is positive. That's sine, which means my answer is negative. Now, I really don't expect you to be able to do that right now. This is where you'll be at the end of the unit. You'll be able to do this maybe even quicker than we just did, but just something for you guys to look forward to. Question 2, a trig application. How long a ramp do you need for a 3-foot high ledge if the angle of elevation is 20 degrees? So the first thing we need to do here, obviously, is draw this situation. Here's our ledge. It's 3 feet tall. We have a ramp that goes up to it. And then here's the ground. The angle of elevation needs to be 20 degrees. So 20 degrees would go here, angle of elevation. How long a ramp? This is the ramp, so that would be our x. What do we notice here? Here's my angle. That's opposite. That's hypotenuse. You've got to recognize that as sine. Sine equals opposite over hypotenuse. So we just set up a simple trig equation. Sine of 20 degrees equals 3 over x. We've kind of talked about this in a proportion. You can interchange the means and extremes, or you can remember that trig video you probably watched in geometry. When x is down low, switch and go. So that equation becomes x equals 3 divided by sine 20 degrees, which you would obviously throw into your calculator. Please make sure you're in degree mode, and that gives me 8.77 feet. Okay, this is important. What is a radian? I don't expect you to remember this. It's probably not done justice in Algebra 2, so we are really going to do a good job in Pre-Calc to make sure you have a thorough understanding before you guys head off to calculus next year. So the definition of a radian is simply a central angle that intercepts an arc equal to the radius of the circle. That is approximately 57.3 degrees. Now, people get confused with a radian because they think it has to have pi in it. A radian doesn't have to have pi in it any more than degrees has to have pi in it. A radian is simply another unit of measure for angles. Kind of like to measure length, we can use inches or we could use centimeters. Those are just two different units of measure. Graphically, here's what a radian looks like. Here's my circle. I have a radius, I'll just make up 3 inches. I'll add another radius, 3 inches. Well, if this is going to be 1 radian, this arc length here, from the end point of that radius to the end point of that radius, has to be 3 inches. Not the segment, the arc length. The symbol for radian is usually RAD. Sometimes you might see a lowercase r. And we've gotten lazy with that. We don't often put 1 RAD. We just put 1, or we put pi, or we put pi over 2. But like we put degrees in angle measures, we really should be putting RAD in for radians. This is the cool part about radian. Here's how it works. Here you can see a circle. Okay, there's my positive x, so that's my initial side. And what I've done here is I've divided the circle up into radians. So this first arc represents 1 radian. This next one represents 2 radians. 3 radians, because if you remember, each one of these is 57 degrees. So think of it as a little bit less than 60. So this is a little bit less than 60. That's a little bit less than 120. That's a little bit less than 180, a little bit less than 240, so on and so forth. So this would be 4 radians, 5 radians, 6 radians. 6 radians would be a little bit less than 360. Where pi comes into play is this. Notice that's 3 radians. That's a little bit less than 180. Well, what would happen if we extend this out to get 180 degrees? What special number do you think that is right there? That's a little bit more than 3 that represents 180 degrees. Well, guess what? That's pi radians. Now, continuing with that, what do you think happens when we go all the way across and we get to 360? This is 6 radians. So what number do you think is a little bit more than 6 that would represent 360 degrees? That's 2 pi radians. That's where pi and 2 pi come into play with radians and why you see that so often. But a radian measure does not have to have pi in it. Here's an example. That right there is just 1 radian, period. There's no pi in that. It's 1 radian because this arc length is equal to the radii. Okay, let's put this into practice. Radian measures of angles. A lot of times we have to make an equivalency between degrees and radians because we are so used to dealing with degrees, but I'll tell you right now, in both pre-calc and calculus, radians are much more efficient to use. So a couple equivalencies here. 180 degrees, you might have learned this last year, is equivalent to pi radians. Not just pi radians. We just established that in that warm-up. 360 degrees is equivalent to 2 pi radians. And here's one thing. If you remember, pi radians is approximately equal to 3.14 radians, right? Because pi is approximately 3.14. So what we'll do now is we'll talk about our special angles. Special angles are angles that we use all the time. They come from a special right triangle, which we'll learn at the end of today's lesson. The first one's called the 45-degree family. So what I have here is a circle, and obviously these would represent 45 degrees. So 45 degrees in the first quadrant, 45 degrees in the second quadrant is 135 degrees. In the third quadrant, it's 225 degrees. And in the last quadrant, fourth quadrant, it's 315 degrees. So how does this work in radians? Well, if we think about this equivalency right here, if 180 degrees is equivalent to pi radians, so that means this would be pi, which means half of that would be 90, so that's pi over 2. Well, 45 is half of pi over 2, so that's pi over 4. So 45 degrees is equal to pi over 4 radians. Oh, all right, so let's label that as pi over 4 radians. So here's what I know. Pi over 4 radians is my first quadrant angle. Well, if this is pi over 4, what's that going to be right there? This distance here is pi over 4, and this distance here is also pi over 4. So how do I come up with this angle measure in terms of radians? Well, I need to understand that this is pi, and I'm subtracting pi over 4. So what do we need to do? We need to get this to be a fraction with 4 in the denominator. Well, pi is the same as 4 pi over 4. 4 pi over 4 minus pi over 4 is 3 pi over 4. That's this angle right there. So 3 pi over 4 radians is our second quadrant angle. Now we're going to play the same game here, except now I'm adding pi over 4. So 4 pi over 4 plus pi over 4 is 5 pi over 4. So 5 pi over 4 radians is my third quadrant angle. And now in the fourth quadrant, all right, that's 2 pi, and I'm subtracting pi over 4. So to get this to be a fraction with 4 in the denominator, you think of it as 8 pi over 4 minus pi over 4. That gives you 7 pi over 4. So that's what my fourth quadrant angle is. So 7 pi over 4 radians is my fourth quadrant angle. So when we talk about a 45-degree family or a pi over 4 family, you need to know these 4 measures. And how do you get those quickly? Well, obviously, if it's just pi in the numerator, you're always in quadrant 1. This here is pi. So always think of it as the numerator and the denominator being the same. So if my numerator is 1 less than the denominator, you're always in quadrant 2. If your numerator is 1 more than the denominator, you are always in quadrant 3. So you'll be able to recognize these quickly without having to think about this diagram. If your numerator is almost twice the denominator, you're always in quadrant 4. We use the quadrants to determine positive or negative when we incorporate ASTC. Okay, let's go through our 60-degree family a little bit quicker. Same concept, so let's talk about our 60-degree angles. That's 60 degrees. This would be 120 degrees. This one would be 180 plus 60, so 240. And then this one would be 300. Now, how does this work? Well, if you think about this concept up here of 180 degrees equaling pi radians, 60 is the same as 180 divided by 3, so 180 degrees. That would equal pi radians divided by 3. So 60 degrees is pi over 3 radians. Okay, so pi over 3 radians is in the first quadrant. Well, this one works kind of nicely because if you think about it, if this is pi over 3, well, that's got to be 2 pi over 3, right? Because I have 2 of them right there. It doesn't quite work the same way as up above, but the other way you can visualize it is that this is pi, and I have to subtract pi over 3. So my denominator now is 3. That would be 3 pi over 3 minus pi over 3. So either way, that would be 2 pi over 3 radians. So these two are equivalent. 2 pi over 3 radians is the same as 120 degrees. So 2 pi over 3 radians, that's in quadrant 2. We already discussed that would be 3 pi over 3. It's not one of my special angles, so I have to go one more. 3 pi over 3 plus pi over 3. Well, that's 4 pi over 3. Okay, so this angle here is 4 pi over 3 radians. 4 pi over 3 radians is quadrant 3. And this one here would be 5 pi over 3 radians. So 5 pi over 3 radians is in quadrant 4. So remember how we just determined whether you're in quadrant 2 or 3. If the numerator is 1 less than the denominator, quadrant 2. If your numerator is 1 more than the denominator, quadrant 3. Because remember, this is equal to pi. So it's 3 pi over 3, it's 4 pi over 4, it's 6 pi over 6. And then if your numerator is almost double the denominator, that puts you in quadrant 4. Our last family we'll talk about, the 30-degree family. So I've got them highlighted here. This would be 30 degrees. This would be 180 minus 30 degrees, or 150. This one is 180 plus 30, or 210. 360 minus 30, 330. So remember that equivalency we talked about? 180 degrees is equal to pi radians. 30 degrees is equal to 180 degrees divided by 6. So that means it should be equal to pi radians divided by 6. So 30 degrees is pi over 6 radians. So pi over 6 radians is our first quadrant angle. So if this distance here is pi over 6 and this is pi, make it a fraction, so 6 pi over 6, subtract that, 5 pi over 6, which follows that pattern we talked about before. The numerator is 1 less than the denominator. I'm not even going to bother with the fractions. I'm going to follow that pattern. In the third quadrant, my numerator is 1 more than the denominator. So this has to be 7 pi over 6 radians. In the fourth quadrant, it's almost double. So 6 times 2 is 12, but you got to subtract 1 from that. So that will be 11 pi over 6 radians. So 5 pi over 6 radians is in quadrant 2. 7 pi over 6 radians is in quadrant 3. And 11 pi over 6 radians is quadrant 4. So there's our 30-degree family. Quick review, coterminal angles. Angles that share the same terminal side. How do we find it? Well, we've got now degrees and radians. So the way we find it in degrees is we take our angle theta and add or subtract 360 degrees. How we find it in radians, which will be a little bit more challenging for you guys, is we take our angle theta and we add or subtract 2 pi radians. So we're going to have to be good with fractions because our angle is most likely going to be something like 2 pi over 3 or 5 pi over 4. And then we have to add or subtract 2 pi from that. We'll do some more of that later on in the unit, but now let's move on to arc length. Now there's a couple approaches to arc length. Conceptually, an arc length is simply a fraction of the circumference of a circle, right? Here's the circumference of the circle. The arc length is only this piece of it. So conceptually, as long as you know your formula for circumference of a circle, and I give you any angle, whether it's degrees or radians, you just create a fraction with that and multiply that by the circumference. Well, there's a couple formulas for circumference. Hopefully you know them both. C equals pi d, which is the one I'll be using. And then there's C equals 2 pi r. I'm not a huge fan of using that because a lot of students get this confused with the area formula, which is pi r squared, because they both have a pi, an r, and a 2. So that's why I stick with this one. But both work, obviously. So here's an example of an arc length question where we don't really need an arc length formula, although there is one. It's a simple one. You guys probably remember it from last year. I'll take a look at this and see, oh, that's 60 degrees. So if I want to find my arc length, what I would do is say, all right, arc length, and the symbol for arc length is S, by the way, so I'll just use an S, is I need to take a fraction. Well, that fraction is going to be this divided by that. So since I'm in degrees, that fraction is going to be 60 degrees over 360 degrees. That's the fraction. What is my circumference? Pi d. All right, so pi d. What's the diameter here? Well, the diameter is going to be 14, so it's going to be this times pi times d. Now, 60 over 360 is simply 1/6, so that's going to be 1/6 pi times my diameter, which is 14. And if I want to put all that together in one fraction, that would be 14 pi over 6. Great. Calculator inactive. Let's simplify it a little bit. 7 pi over 3. That is my arc length. That is your x, if you will. Guess I should have used an x there. Okay. Now, obviously, if you wanted to, you could multiply that out and get a decimal equivalent, but I think it's much cleaner just to leave it like that. Our next example. Again, I want to find the arc length, x. And notice my central angle is 2. It's not 2 degrees. All right. Now, technically, this is a little bit lazy. We should put r or radians in there as well. That's in radians. If you don't see a degree symbol, it's radians. Remember, radians does not need to have a pi in it. So, how do I find x? It's a fraction of the circumference. What's that fraction going to be? Well, the numerator of that fraction is going to be 2, because that's this angle here. What's the denominator? What's 1 revolution in radians? Well, remember, that's going to be 2 pi radians. So my fraction will be 2 over 2 pi. My radius is 8, so my diameter is 16. Just plug that in. X equals 2 over 2 pi times 16. Now, this is why radians work out nicely, because when I do this, these pi's cancel, the 2's cancel. Wow, that's just equal to 16. That's kind of cool. So maybe we can derive a formula here. How else can I get 16 using these numbers? Isn't 16 just 2 times 8? That's how we create our easy arc length formula. S stands for arc length equals the central angle, theta, that was our 2, times r, the radius. In this case, r stands for radius. However, there's a catch. This only works when theta is in radians. Must be in radians. Okay? So, that's an easy formula to work with. If my central angle is in radians, great, I use that. Very easy. However, the issue is sometimes we have a tendency to forget theta has to be in radians. So I get to a question like this, I'm like, oh, well, I'm just going to use 50. You can't use 50. We need to convert it first. So here's how I'd approach this one. It's an arc length question. S equals theta r. S in this case is the arc length, 18. So here's an example of one we have to work backwards. All right, so I plug an 18 in here, equals theta. I'm going to hold off on that, and I'm finding r. So since your theta must be in radians, we need to convert 50 degrees to radians. So the way we do that is we multiply by pi over 180 degrees. Why do we pick this fraction? Because pi radians divided by 180 degrees is equivalent to 1. We're just switching the units. So if we do that, let's cancel zeros. I get 5 pi over 18. That's what I'm going to plug in here. Okay, so let's bring that over. 5 pi over 18. To solve for r, I simply need to multiply by the reciprocal. So let's multiply both sides by 18 over 5 pi. 18 over 5 pi. And what does that give me? Let's see, 18 times 18, I got to look that one up, is 324 over 5 pi. So that would be my radius. If this is calc inactive, I just leave it like that. There's my exact answer. If I want it to nearest tenth or something, obviously you can just throw that into the calculator. Okay, let's try one more. And here you can see that my central angle is already in radians. So I'm thinking, okay, S equals theta r. You don't have to write that every time. I'm just showing you where we're getting our numbers. The arc length is 8. My central angle is pi over 3. And I'm solving for r. Again, we're just going to multiply by the reciprocal. 3 over pi, 3 over pi. So what does that get us? Let's see. R equals 3 times 8 is 24. 24 over pi. Again, that's an exact answer, which is the type of answer you'll be asked to find most often. And just leave it like that. If you wanted a decimal equivalent, obviously you can just put that into your calculator. Lastly, we're going to finish up with our special right triangles, starting with our 45, 45, 90. So in this triangle here, obviously that's my 90-degree angle, and I've got two 45-degree angles, which makes this an isosceles right triangle. These two have to be the same. What I want to do is denote each one of those with length 1, because what I want to do is come up with a ratio of the three sides. Here's one easy way we can do it. Use Pythagorean Theorem. 1 squared plus 1 squared equals x squared. 1 plus 1 is 2. 2 equals x squared. Take the square root. X equals square root 2. And that's true. But watch what else we can do. It doesn't matter what these sides are. This hypotenuse will always be one of the sides times square root 2. So you can predict what this triangle would be if this is a 45, 45, 90 right triangle, and these are 7. That means this has to be 7 square root 2. You can do it quick. Why does that work? Well, check this out. If I pick a triangle, and let's say 3, 3, and x. Okay, set this up. 3 squared plus 3 squared equals x squared. Here's some cool algebra. 3 squared plus 3 squared is the same thing as 2 times 3 squared. Well, let's now take the square root. Well, here's a property of radicals. This you can simplify and bring out front as a 3, so that ends up being 3 square root 2. Now, I'm guessing you guys can figure out that this is going to work every single time. So no matter what these sides are, that number is going to come out in front of your radical, and you'll always have a square root 2 attached to it. So that's kind of a simple way that we can find that hypotenuse anytime we're giving an isosceles right triangle. But more importantly, we are going to use this ratio to come up with sine, cosine, and tangent of 45 degrees. And our second one, our 30, 60, 90 right triangle. You guys might be looking at this and saying, that's not a right triangle. That looks equilateral. And you are correct. It is equilateral. So this is 60 degrees. That's 60 degrees. Why would I start with an equilateral triangle? Because I want you to draw an altitude from that vertex. Now, because this is equilateral and those are 90 degrees, each angle up here now obviously is going to be 30 degrees. Let's represent this smallest side as 1. Well, remember from geometry, not only is that an altitude, but it's a median and an angle bisector, so this side over here has to be 1. Since it's an equilateral triangle, if this entire length here is 2, that means this length here has to be 2. So now all that's left for us to do is find this side. Okay, well, this is a leg, this is a leg, that's my hypotenuse, so let's use Pythagorean Theorem on that. 1 squared plus x squared equals 2 squared. Subtract 1 from both sides, x squared equals 3, square root it, x equals square root 3. So this side here is square root 3. So once again, I'm not saying that every 30, 60, 90 right triangle has sides 1, 2, and square root 3. But every 30, 60, 90 right triangle has sides in the ratio 1, 2, square root 3. Remember, similar triangles, sides are in proportion. So I don't really think of this as an equilateral triangle. Basically, what I want you guys to do is be able to pull out the 30, 60, 90 right triangle. All right, so there's my 60-degree angle. There's my right angle. There's my 30. The smallest side, so the side opposite the 30, is always 1. All right, I'm talking about a ratio. The longest side, so the hypotenuse opposite the 90, is double that, 2. And the middle side, opposite the 60, is always square root 3. So what would happen is if I make this side here 5, the hypotenuse is double that, 10, and this side is 5 times square root 3. If I make this side 7, well, then that would be 14, and this would be 7 square root 3. So that's kind of how that ratio works. And again, what do we use this for? We use it to find sine, cosine, and tangent of 30 degrees and of 60 degrees. All right, guys, that concludes day 2. I know there's a lot here, and that's why I'm strongly encouraging you guys to do the homework assignments associated with these lessons. Check your answers. Start memorizing these values. You have to know these. You have to know your radian families. You have to be able to visualize that circle to determine a STC, where these functions are positive, where they're negative. But we'll get through it. We'll get through it for sure. As usual, guys, if there's any questions, don't hesitate to reach out and ask, and we'll see you in class soon. Thanks for watching.